All right, let's talk next about unbiasedness of the estimators and specifically the ordinary least squares estimators for which we just have derived the coefficients. And let's first clarify what unbiasedness means. So an unbiased estimator is a statistic whose average is true to the population parameter when the sampling is repeated an infinite number of times. So imagine this, if we were able to take 1 million samples of size n equals 6 from a population with a true relationship between y and x given by yi equals beta 0, that's the population intercept, plus beta 1, which is the population slope, times xi, plus ui, the residual, then an unbiased estimator would be 1, where the average of all 1 million sample regression intercepts A and sample slope coefficients B would be equal to beta 0 and beta 1. So, in other words, what we try to show when an estimator is unbiased is that the expected value of A in many samples is equal to the population intercept, and likewise the expected value of all possible sample slope coefficients is equal to the population slope beta 1. Let me give you another example that is easier to grasp the concept of unbiasedness. So the mean, for example, is an unbiased estimator. So let's consider the following example. Let's say we have a population, and the population only consists of 3 children, A, B, and C. And they have a characteristic xi, and a characteristic BH, let's say. And let's say kid A is 4, kid B is 6, and let's say kid C is 14. Well, then the population mean, and the population mean would be abbreviated with a Greek letter of mu, which looks something like this, like an M with a long left tail. Well, that would be 4, 10, 24 would be 8. So that is a population parameter. The population parameter is 8. So now let's think that we take all possible samples from that population of A, B, C, but each sample consists of only 2 observations. So then I can get in total 3 samples. Sample 1 is A and B. And sample 2 would be B and C. And sample 3 would be A and C. So now what is the sample average of each sample x bar? Okay, A and B, 4 and 6 over 2, so that would be a sample mean of 5. X bar is 5. Sorry. Then for B and C, 6 and 14, 10. So that sample mean would be B and C, 10. The last sample, A and C, 4 plus 14, that's 8. That averages out to 4 and 14, 18, 9. Okay, so now what is the average of all those sample means? So we will say the sum of all the possible sample means I over 3. That is 5 plus 10 plus 9, 24 over 3, which is 8. So the average of all possible sample means is equal to the population parameter, and whenever that condition holds for a statistic, then we call the estimator unbiased. And the mean is an unbiased estimator. And what I want to show you next is that the sample regression intercept and sample regression slope coefficient, they are unbiased too. So again, what we are trying to show is that the expected value of A is equal to beta 0, and the expected value of B, that is equal to beta 1. So now here on that slide, I have already derived the proof, but I also want to just go over it quickly separately and explain some important steps. So what we try to prove is, we try to prove that the expected value of B is equal to the true population parameter beta 1. And we start with the slope coefficient because if you remember, the solution for the intercept was A equals y bar minus B. So we need to have B first. It was y bar minus B times x bar. And again, we know that in the population, yi is given by the population intercept plus the population slope coefficient times xi plus some residual. Okay, so somehow what we need to do is we need to incorporate that relationship into our formula for the slope coefficient. And if you remember, the slope coefficient was given by B equals to the covariance of x and y over the variance of x. Okay, so we can write the covariance of x and y once like this: xi minus x bar. This doesn't look too nice. So xi minus x bar times yi minus y bar. So that is the product of all the deviations of x and y from the mean. And then we divide that by the variance of x, and that is the sum of xi minus x bar squared. Okay, so now we do acknowledge a thing that in this case we can rewrite the covariance actually differently too. And what we can do is we can rewrite the covariance. We look at the yi and we just multiply yi times what we see here in parentheses to the left. So I just can multiply through. I can say this is equal to yi times xi minus x bar. So I just multiply basically yi times this term. And then I can also do the same thing for minus y bar times xi minus x bar. Okay, so that's all next to the sum sign. Okay, so now if I want to put the sum sign in front of each, I can actually also write it like this, where I take this term quickly here and I put it a little bit to the right. And because y is a constant, I can put the sum sign in front of this one. And everything is still above the variance of x, which is sum of xi minus x bar squared. Okay, but the point here is that the sum of all the deviations from the mean, that is always 0. So this term, this sum, is equal to 0. And we can actually see that if we quickly go back to our sample. So here we had a mean of 8, and then if we calculate xi minus the mean, then we do 4 minus 8, negative 4, 6 minus 8, negative 2, 14 minus 8, plus 6. And you see that negative 4, negative 2, negative 6, plus 6 is a 0. And this is what we basically see here. So we can write the equation just like this. Okay, so now we introduce another simplification. And what we assume is that all the variation of the intercept or the slope coefficient, that is driven by variation in the dependent variable. So what we do is we assume that we always take the same sample characteristics. So for example, if I want to study the relationship between a person's shoe size and their height, there's probably a positive relationship that people with longer feet, they are taller. But now what we assume is we always get the same 6 people with the same shoe size. So we always get somebody with a shoe size of 8 and a shoe size with 9 and a shoe size of 10 and 11, 12 and 13. So they always have the same sample, but the difference is in the y. Of course, that's a simplification, but that's what we do. And if we do that, what happens is that we can assume this term here, we assume that is always the same. And we call that Ki. Okay, and here the sum of xi minus x bar squared, what we have here in the denominator, that's the variance of x. And yeah, and in the numerator we have always the deviations from the mean. So with this simplification, or with this abstraction in mind, we can actually write B as the sum of yi times Ki, and keeping in mind that Ki is what I circled here in red. Okay, so next what we want to do is, because we want to show that the expected value of B is equal to beta 1, well, I have B to the left side of the equation, and I have here now yi. Well, all I need to do now is I need to replace yi by the formula beta 0 plus beta 1 times xi plus ui. So B can be written as the sum of beta 0 plus beta 1 times xi plus ui times Ki. And now I multiply through, and then that is equal to the sum of, okay, beta 0 times Ki. Let's do it one more time. So then it becomes beta 0 times Ki plus beta 1 xi Ki plus ui times Ki. ki. Okay, but now I write everything in sums wherever I can sum it up. So wherever you see a plus sign, I can put the sum sign also in front of it. And that means we can write b now as, and remember, whenever you have a constant, that goes in front of the sum sign. So the sum of beta 0 times ki, that can be written as beta 1 times the sum of ki plus beta 1, 1 not I, beta 1 times the sum of xi times ki plus the sum of ui times ki. Okay, so now we just take a look first of the sum of ki. Okay, so ki is xi minus x bar. If you sum that up, so then we have here the sum of xi minus x bar over, and because that is a constant down here, I just can write it like this, 1 times 1 over the variance of x. We don't need that for now. What's important is the sum of xi minus x bar, and as you already know, all the deviations from the mean, well, they are equal to 0. So this term evaluates to 0. So let's move to the next one. So we have here beta 1 times the sum of xi times ki, but I put that again in front, so we can write beta 1 times 1 over the variance of x so now I need to sum up the sum of xi times xi minus x bar. Well, and this term is again equal to the variance of x. Why? So let's remember that the variance of x can be written as the sum of xi minus x bar squared. But I don't write it as squared, I multiply through. Okay, so then you know I can just write this is equal to the sum of xi minus this one, the second term. I can write it as xi times xi minus x bar plus, now the second term is the sum of, oh no, let's just do it. So plus x bar times xi minus x bar. Okay, but now I can put the sum sign again individually in front of each. So then that is the sum of xi minus x bar plus x bar times the sum of xi minus x bar. And as you know, that this is again 0. So this is again 0. So we can just write the variance of x as the sum of xi minus x bar. So in other words, we have here the variance beta 1 times the variance of x. So times the variance of x. So this cancels out and we just have here beta 1 because this term evaluates to 1. Okay, so now the last one is the sum of ui times ki. So here this also evaluates to 0. And the reason is that it evaluates to 0 because we assume that when we always have the same x values, so we assume we always have more or less the same sample. So we have here the x and here the y. We always have maybe the same axis, and maybe we have a trend line like before, which is maybe 3 here, and the slope is 1. Well, what that basically says is, sometimes at any xi, sometimes the residual is positive, sometimes it's negative, but it cancels out to 0. And then again, maybe it's positive, then it's negative, maybe here it's negative, the next time it is positive. So there is some variation, but it can be assumed to be evaluating to 0. Sometimes it is positive, in the next sample it's negative. So this always evaluates to 0. It seems to be plausible once you if you think yourself into it, but it cannot be maybe as easily proven as this one. But the residuals, they are normally distributed around the trend line, and then whenever we evaluate the deviations from the mean, that xi minus x bar eventually will be equal to 0. So we also write that one, that this term, the sum of ki, is evaluated with the expected utility of ui, and that is equal to 0. So that this final term evaluates to 0. Whenever you evaluate something with the residuals, it evaluates to 0 because we assume everything, positive and negative residuals eventually cancel out. And so whatever you multiply with the residuals, that will evaluate to 0. Okay, so now we know that the first term evaluates to 0, the final term evaluates to 0, and the sum of xi times ki evaluates to 1. So we can see that b can be expected to be beta 1. And this is what I also have basically here, actually here. And so now we have shown that the expected value of the sample slope is indeed equal to the population slope. All right, so okay, so we are done with this one. The next one that we try to evaluate is that we want to prove that the same holds for A. So we want to prove that the expected value of A is equal to beta 0. And again, what we need to do is, so we know that A is equal to y bar minus b times x bar. So if we somehow need to get into this equation the fact that we need to get the variation in y into it, and yi is beta 0 plus beta 1 times xi plus ui. So this is what we need to get into here. The way to do that is we start with a trick. We start and multiply both sides by n, and then we get here na equals n times y bar minus n times b x bar. Okay, so now n times y bar is nothing else but the sum of all the yi's that I have. Okay, so now we can say that NA equals n times y bar, so I replace this term by yi, and minus n times, and b, we already did the expected payoff of b, so the expected payoff of b is beta 1, so times beta 1 times x bar. And that can be also written as the sum of yi, before I insert this one, minus n is a constant and x is and beta 1, n times x bar, can also be written as beta 1 times the sum of xi. So n times x bar, just like as n times y bar, equals the sum of yi, n times x bar is the sum of xi. Okay, so but now we need to insert for NA, at NA, for the sum of yi, we can write now the sum of, beta 0 plus, so there's a parenthesis around, beta 1 times xi plus ui minus beta 1 times the sum of xi. Okay, so now we have, so we can write that again differently. So we can write now the sum of beta 0, so that's just n times. If I sum up beta 0 n times, it just gives you n times beta 0 plus beta 1 times, so that's a constant, times the sum of xi plus the sum of all the residuals minus, and here we already have that, beta 1 times the sum of xi and a. So now we see we have here beta 1 times the sum of xi minus beta 1 of the sum of xi, so that already cancels out. Well, the sum of ui, the sum of all the residuals, has to be equal to 0, because OLS minimizes the squared deviations from the mean, so the positive and negative values will have to cancel out. So that means that this term evaluates to 0. So that means we are left with NA equals n times beta 0, and then we divide both sides by n, and we see that we can expect A to be equal to beta 0, which is what we wanted to show. So both the intercept and the slope coefficient can be shown to be unbiased estimators. And I have that also again here on the slides where we derived everything as well. So if you want to just look at the slide again and it makes clear, that should be fine. But I hope that I could explain it as well too by deriving it again step by step. So this is the unbiasedness of the estimator. So let's just stop here, and then we have one more final thing to derive, which is also something that all regression or all statistical software programs report, which is the standard errors of the regression coefficients, but I do that in a separate video. So let's just stop here, and we discuss the standard errors of the regression coefficients in the next video.